Welcome to this talk on investigating lubrication by using Stribeck-like curve and ultra-low wear test method. It is known that a significant part of the fuel energy is consumed by friction between the moving parts. Engine, for example, has several moving parts like piston assembly, valve train assembly, and engine bearing. Here, an engine oil is used to lubricate and cool these moving parts. For this purpose, engine oils with different grades and a variety of brands are available in the market that caters to the needs of any lubrication mechanism. Generally, lubrication mechanism can be well described by Stribeck curve. Here, the friction coefficient and lubricant film thickness is mapped against the Hersey number, that is, a function of lubricant viscosity, speed, and pressure. Starting from the right side, where the friction coefficient is the lowest, is called as hydrodynamic condition. In this state, the surfaces are completely separated by a thick film. As the speed decreases, the film thickness will reduce and there is an increase in surface contacts, leading to higher friction. These regions are called as mixed and boundary conditions. Such a curve is widely known as Stribeck curve or sometimes Stribeck-like curve. Friction of moving parts in an engine results in a loss of 12% of fuel energy. Using the data from Kenneth's paper, we can distribute this loss over 3 different lubrication regimes. Hydrodynamic lubrication state in piston assembly, engine bearings and pumps account for 48% of this loss, which stands as the tallest of all. Mixed lubrication, that is, including elasto-hydrodynamic lubrication and boundary lubrication, account for 37.5% and 4.5% respectively. Research work that investigates the role of friction in fuel consumption should be appreciated because it is focused on solving a bigger problem, that is climate change. Decrease in the fuel consumption will reduce the pollution, hence we can control global warming and its related adverse effect on the society. In this line of thought, a minor effect but a significant contribution can come from switching to low viscosity grade engine oils. The rationale behind it is that higher viscosity engine oil requires more energy to shear compared with low viscosity engine oil. Theoretically, the power loss in piston assembly and engine bearing or journal bearing is directly proportional to the square root of engine oil viscosity. Not to forget that hydrodynamic lubrication gulps a significant part of fuel energy in an engine. Therefore, switching to low viscosity engine oil will not only reduce power consumption, but it could also improve fuel economy. In this preliminary study, we have looked into the pros and cons of switching from high viscosity engine oil, that is 10W40, to low viscosity engine oil, that is 5W30. We assume that lubrication regimes at various engine components can be reproduced using a model test such as Rotary Tribometer for this purpose. we have selected two fully formulated and commercially available engine oils, SAE 10W40 and SAE 5W30. Kinematic viscosity that represent the internal resistance to lubricant flow at 100 degrees Celsius is 12.2 centistokes for 5W30 and 14.3 centistoke for 10W40. It might mean that pumping or sharing of 10W40 consumes more fuel energy compared to 5W30. Another important lubricant property, that is high temperature, high shear viscosity, represent the resistance to flow at confined spaces at 150 degrees Celsius, like examples of piston ring and cylinder and engine bearing. High temperature, high shear viscosity is 3.5 centistoke for 5W30, but we could not find any value by the manufacturer of 10W40. Ducom Rotary Tribometer with a ball on disc configuration was used to measure friction of engine oils. Load, either by dead weights or computer controlled, is applied via a lever that holds the ball. As the load is applied, ball is pressed against the sliding disc. Friction force acting on the loading lever is measured using a load cell at a resolution of 100 millinewton. Contact pressure was fixed at 1.2 gigapascal. This we call it a high contact pressure test. The lubricant volume was 3 milliliter. Lubricant was heated to 80 degrees Celsius through induction heating of the disc. All the controls and data acquisition system is via Ducom software, which is a LabVIEW based system. Now, how to use a rotary tribometer to generate Stribeck-like curve? Advanced motion control system in the Ducom Rotary Tribometer enables the control of sliding speed. In this case, we input an exponential decay function to control speed as a function of time. As you see, the initial speed at 1500 rpm decays over time to final speed of 100 rpm. Simultaneously, the friction force is measured and displayed. An idea is that there is continuity of events like lubricant film build-up and breakdown, which should be strictly influenced by speed in a model test method like Ducom Rotary Tribometer. Let us look at the friction results represented by a friction versus sliding speed graph. For 10W40, as the speed decays, the friction tends to increase. After 0.7 meters per second, there is a substantial increase in friction as the speed is continuously reduced. The point where a jump in friction is observed is considered to be the transition point, representing asperities coming into contact. Similar friction behavior is observed for 5W30. However, the transition occurs at a later stage and the friction coefficient is 10% lower than of 10W40. Earlier results were from a high contact pressure, that is 1.2 gigapascal test. We also did a friction test at low contact pressure. Low contact pressure was achieved by micro-polishing the ball. We call it as flattened ball. Here, the contact pressure was 7 megapascal approximately, which is lower by 2 orders of magnitude compared to high contact pressure test. Such low contact pressure is expected in journal bearings at low engine speeds of 500 rpm. Another important advantage of a flattened ball test is that we get a larger shearing area of lubricants. Here we look at the friction versus sliding speed graph for low contact pressure test. For 10W40, the friction coefficient is stable, although the speed is changed from 2 meters per second to 0.7 meters per second. After 0.7 meters per second, the friction coefficient jumps and increases substantially until the end of the test. Similar behavior is observed for 5W30. However, the transition from stable to high friction is at a later stage. Friction coefficient for 5W30 is 60% lower than 10W40. Please note that all the tests were repeated 3 times for statistical significance. This model test, that is, using rotary tribometer with either high or low contact pressure, shows that more energy or power is required to shear through high viscosity engine oil compared with low viscosity engine oil. Model test shows that friction is reduced by switching to low viscosity engine oil. If this could be true for an engine, then a significant reduction in fuel consumption is expected, because an engine with hydrodynamic, mixed and boundary friction consumes approximately 10% of total fuel energy. Using this thumb rule of 10% fuel consumption by an engine and friction reduction by low viscosity engine oil as per our model test, we deduce that a maximum fuel saving of up to 0.47% is possible by switching to 5W30, that is a low viscosity engine oil, from 10W40, which is a high viscosity engine oil. Well, how does this friction and fuel savings by 5W30 replacing the 10W40, a high viscosity engine oil, would stand with respect to the available literatures in public domain? At first, we looked at the field test results, that is, fuel consumption by buses driven by CNG. After 30,000 kilometers, the total fuel consumption by buses using 5W30 engine oil was 3.7% lower compared to buses that were lubricated by 10W40. Now, following the thumb rule of 10% fuel consumption by an engine, we can say that 0.37% of fuel is saved in this fleet test or the field test by switching to low viscosity engine oil, that is 5W30. The fuel saving determined by model test and fleet test are in the same order of magnitude. This specific case could be a coincidence, however, indicates that there is no conflict between model test and fleet test. Apart from our model test, even a comparison with a set of different model tests widely used in research can provide more insight. A comparison is made by using a friction coefficient versus model test graph for engine oils 10W40 and 5W30. A linear reciprocating tribometer with a piston ring on cylinder interface at a contact pressure of 1.2 megapascal and at a frequency of 7 Hz showed lower friction for 5W30, that is, average friction coefficient of 0.092 compared to 0.098 as determined for 10W40. Similarly, a mini traction machine at a contact pressure of 1.9 gigapascal showed lower friction coefficient for 5W30 compared with 10W40. As you see, the friction coefficient determined by Ducom Rotary Tribometer with pure sliding contact is comparable with other model tests. In general, all the model tests indicated low friction coefficient due to switching from high viscosity engine oil to low viscosity engine oil. Importantly, the low contact pressure test by using a flattened ball in Ducom Rotary Tribometer thus determined fuel saving was closer to the fuel saving obtained from the fleet test. With all this information, we are not trying to pretend that model test is an alternative for field test. Model test is what it is. Reproducing the dynamics of an engine using a model test like rotary tribometer is not completely possible. However, the model tests are beneficial in several ways. Different components in an engine experience different friction conditions such as hydrodynamic, mixed and boundary. All of them can be reproduced in ball-on-disc type model test. Model test, its ability to measure the lubricant's behavior in hydrodynamic, mixed and boundary friction condition is useful in quick screening of lubricants for field tests. The time and cost is significantly lower compared to the field test. Furthermore, we should also look at other side of this discussion, that is, wear. In this study, at high contact pressure, the mean wear scar of the ball is in the range of 300 to 350 microns. However, at low contact pressure, by using a flattened ball, we measured approximately 3 orders of low wear. Interestingly, there was no wear measured for 5W30 as determined by using an optical microscope for measurements. Therefore, this flattened ball test in a rotary tribometer qualifies to ultra-low wear test method. Note that the wear of 2000 nanometers measured for 10W40 is still 200 times higher than wear measured in an engine. Again, this wear data should remind us that a careful use of model test is only a precursor for field test. We are coming to an end of this presentation. The conclusions are the following. A Stribeck-like curve is generated using a decay function in the Ducom Rotary Tribometer. It is used to show that low viscosity engine oil, that is 5W30, reduces friction compared with 10W40. By flattening the ball, we reduce the contact pressure to 7 megapascal and increase the shearing area. This substantially improved the distinction of 5W30 compared to 10W40. Interestingly, our friction coefficient values were comparable to the other model tests in the literature. Friction coefficient was used to predict the fuel savings. Thus, predicted fuel saving using the model test, including that of Ducom Rotary Tribometer, was comparable to the fleet or field test results. This case could be a coincidence, however, it is interesting enough to aspire for more experiments to improve our understanding. Furthermore, the measured wear using model tests is 2 orders of magnitude higher compared to an engine wear. We are also running a long duration test for 25 hours using a Ducom shear stability tester, widely known as KRL test according to CEC L4599. Here, an engine oil is circulated through a tapered roller bearing at 60 degrees Celsius, axial load of 5000 Newton and speed at 1450 rpm. Using these operating parameters, we acquire friction torque behavior of engine oils over a duration up to 25 hours. As you see in these results, the friction torque of low viscosity engine oil, that is 5W30, is lower than high viscosity engine oil, that is 5W40. Here we didn't use the 10W40 engine oil, this is still in progress. However, an interesting observation is, although low viscosity engine oil shows lower friction, but it is not stable compared to 5W40. Overall, there are several benchtop tribometers that are known as model test, which could be very useful in development of fuel-efficient lubricants. I will end this presentation by expressing my thanks to all the contributors to this presentation